thing. What goes here? Thing. I like using my formal mathematics. Okay, what's the next one? In fact, I'll be more specific, the 1 factorial. What's going here? Thing squared, and I want one more term only. I just said the first 4 terms. Notice I said, this time I said terms, not degree. Okay. I'm stopping there, therefore, this becomes an estimation. It is asymptotic. It is absolutely not equal. I've got an x to the 9th power there. I'm going to be working with really small decimals on x to the 9th power. That's part of the reason we know these numbers are going to get really, really small, aren't they? Really, really fast. So let's simplify this first. Okay, I do not want to integrate things that look like that. That would just be horrible. Where did I write this one down? Here we go. So I want to integrate that. So first thing I want to do is simplify all that stuff. Is that right?
Yeah.
3/4 divided by 2, so that's going to be 3/8, x to the 6th. 15/8 divided by 6, would that be 5/16? X to the 9th. I think we're good. Use your fraction key. I'm a big fan of fraction keys. Okay, this is my estimation of that, just to be safe. And again, just to be certain that we didn't totally booger this up. That's a math term, as you know. Actually, it's right this way. Okay, so that's that guy. Ooh, that's a crazy looking curve, isn't it? Mm-hmm. By the way, what's up with that? This is -1, by the way. I have a vertical asymptote.
Yeah.
Oh. And I am defined on the other side. Oh, although I don't. That's it. Oh, I'm sorry. No, I'm not. That's never mind. That's square root. Sorry. I couldn't tell what root I am. Isn't that cool? I got a vertical asymptote there. Is that going to bother us? No, because we're on the right side, as opposed to the wrong side. No, we're on as opposed to the left side. Because I asked you to go from what to what? 0 to 0.1. So I'm actually asking you that little sliver right there. Well, look at that. That's 1 unit height. Isn't that going to be around 0.1 when we're all done? That seems reasonable. That our answer should be around 0.1 when we're all done. It's not going to equal 0.1. I think it'll be more or less. The curve's starting to come down. Oh.
That's still centered, don't worry.
Sorry?
It's still centered.
Oh,
Yeah.
no, we turned off for a second there. So we probably a tiny bit less, okay? Let's integrate this thing then. So now here's what I want to do. From 0 to 0.1, let's do the integral. All right, so this should be relatively simple. So it's going to be x minus an 1/8 x to the 4th. So 3 over 48, so plus a 16th. I'm sorry, not 48, sorry. My bad. 3 over 56, sorry. X to the 7th, and then minus 5 over 160, which would be 1 over 32, x to the 10. I have 0.1 going to be raised to the 10th power and then divide by 32. That's pretty small, isn't it? That's 12th decimal place. But the next term is out even further. So let's do this calculation. Okay. Anybody got a number?
Yep.
Read your number off to me.
0.099987505535.
Oh, how'd you get those extra? My calculator stops at 05, but actually I calculated on a more powerful calculator. Yes, it is 3.5. That's only 11 places. It actually is accurate to 13. But you'd need something more powerful to get the extra decimal places. Is that cool? Yeah, we did 4 terms. Tell me one of the reasons it's so powerful. Large exponents help. And what's the other thing? Small values that you're using. If I had used larger numbers, would I have the same degree of accuracy? Realistically, if I use larger numbers in my integral as limits of integration? No. Obviously, I wouldn't be, but it would still be very accurate, just wouldn't be as accurate. The problem that we did earlier, we were only accurate to 4 places, but we also used much larger numbers, and we only still used, 3 terms? Okay? So what is the point of what we're doing? The point is, very specifically, is to integration. If you have an integration of anything that can be converted conveniently, that's the key, conveniently to a series, then it doesn't matter if that thing has an antiderivative because you can integrate the series every time. Now, what things do we know the series for in general? In general, we know the series for e to the x, sine x, cos x, log x, inverse tan x. And I think I derived most of those in class. Therefore, any tweakage of any of these things, we then know the series of. And we've been working with all of them to some degree. Now, if I give you an integral that cannot be integrated, I can use the power series and give you an answer in a series form. That may or may not be useful to what you're doing. But in reality, okay, Calc 1, you did a lot of integration, and then you did a lot of definite integrals. In this class, have we done a lot of definite integrals? Think about it. No, in our methods of integration, the first test, hardly had any. Why? Because you're learning how to integrate. You're learning techniques of integration. Tell me an antiderivative. The idea of now evaluating that antiderivative, that's literally below pre-algebra level mathematics. I'm taking a number and I'm plugging it in. That's not mathematics anymore. That's get out a calculator and just raise 1 to a power and write down the answer. Evaluating a definite integral isn't even like calculus. It's barely arithmetic. I'm not joking. It's arithmetic. So our focus was on getting the correct antiderivatives. Calc 3, you're always going to be giving numerical answers because you're always answering questions. You're not interested in just an antiderivative anymore because you're not learning any new methods of integration. You're now saying, what is the volume, or what is the surface area, what are the things like this, okay? What is the work done? Oh, okay. How many have physics right now? Do you ever integrate physics? So some of you shaking. Yeah, hopefully you do a little. Do you ever leave your answer as a general antiderivative, or are you always evaluating that answer? You're always. In real life, you're never going to give an antiderivative for an answer. Sorry. No, you're never going to give an antiderivative. You're going to evaluate the antiderivative. Because every time you ever do an integration in real life, that's what you do when you're not in the classroom, you're always answering a question. Work, surface area, volume. You're giving me an answer. You did all the calculus. You did the hard part. Now just plug in the numbers. So therefore, what we're doing, yes, it's cool that we can give an antiderivative in terms of a series. That's really cool. But in reality, it's always going to be a decimal approximation of that answer because you're answering the question. In this case, I'm simply saying literally, what's the area under the curve? So the most important part, obviously, is to be able to get the antiderivative in terms of a series. But really, I need you to evaluate, which is why, in this case, we didn't actually even need to use whatever the Taylor series or power series or binomial series in this case was. We just said, let's just do the first few terms because we get ridiculous decimal accuracy. So this is one of the only areas in this class where we actually are interested in the answer to the definite integral, because we already have all the techniques of integration we're ever going to know. There aren't any new ones. Everything you learned in the first few weeks of class are all the ones that exist. Everything else is just how to apply them. But now you realize, oh my God, there's an infinite number of problems out there that can't even be integrated. But that's where the power series comes in. But they say, again, the form. What if I replaced x with a function of x? The power series won't help then. So the power series won't help. Why? I can't be putting like sines and cosines and e to the x's in there. The power series is very specific. You're giving me a polynomial that's asymptotic to the original transcendental. But again, it's really the big five. There are other ones you can do. You can do the hyperbolics. You can do an inverse secant if you want. It's just trying to find a pattern using a Taylor series it's pretty gnarly. And in reality, the farther you go in mathematics, and I don't say this jokingly, if you go to my differential equations class and say, Mr. Brown told me to ask you, what are the big four? We use that term every single day in class. Anybody want to guess what the big four are? E to the x, sine x, cos x, polynomial. What about all the other functions? Yeah, they occur occasionally. Probably significantly less than 1% of the time. More than 99% of the time, all the problems you will ever do are one of the big four. That's why it's unnecessary to worry about the fringe things. The thing, the inverse hyperbolic cosecants, Never actually run across one in my entire life, but if I did, I'd look it up probably, because it's not relevant. But e to the x, probably should know well. Sine x, cos x, anything polynomial related, you should know well. So the power series that we're looking at are basically the big three, sine, cosine, and e to the x, are really the big three that we do over and over and over again. And if I can write them as a series, life is good. Now, we haven't spent a lot of time on like the natural log, for example. Right? That is actually a powerful one, but it's very, very specific. So I'm now going to go backwards a little bit because I told you this result a while ago, but I don't think we ever actually showed it. Now, the harmonic series, the big, capital harmonic series. We know this is infinite. We derived it in class by, remember, grouping things into 2 to a power. It was a really, really clever way of showing that this grows without bound. But if you do the integral test on this, it's a lot faster, it's a lot easier. But we know this is infinite. Okay? Everybody cool with that? This is the one that we find more interesting. This one's actually more interesting because we also proved in class that this converges. Now, whether you do -1 to the n or -1 to the n plus 1 is not really the issue. I would like to actually calculate this. How would you calculate this? It actually is equal to a number at some point. I can't integrate it. You can't integrate -1 to the nth power. But, I would like you to all consider this, because we haven't spent a lot of time on things that are centered about 1. We did when we did the square root or the cube root function of x. But we did that as a Taylor polynomial. We never actually found a series. We just did the first few terms. I would like to actually find this as a series. Everybody okay with that? Let's do this. Because it, again, will help us understand the bigger picture, because this is a very specific one. So let's do the first few derivatives. So we're going to find the Taylor series, in other words. I think I'm probably okay by the time I get to the fourth. So first derivative is
1 over x.
second,
1 over x squared.
and the third,
1 over x cubed times 2.
2. And then the fourth,
6
6. 1, 2, 6. The next one's going to be a 24. What pattern is emerging?
Factorial.
Factorial. You might need to do one more derivative, but if the next one's going to be 4 times 6, and the next one's going to be 5 times that, and so on. Aha. Now, f of 1, f prime of 1, f double prime of 1, f triple prime of 1, f fourth derivative evaluate at 1. Okay, f of 1 is 0. Ooh, that means there's not going to be a constant term for this one. This power series has no constant term. F prime of 1, f double prime of 1, f triple prime of 1, f fourth 1. What is my goal? I'd really like to know what's the nth derivative evaluated at 1. Do you think you see a pattern? Well, I think the last one might be easy. If you think of this as the negative of 3 factorial, oh, and this is 2 factorial, oh, and this is the negative of 1 factorial, and therefore this would be... Do you see a clear pattern? Well, there's going to be a negative 1 to the something. What's strange about this one? Isn't it usually negative 1 to the n? Except this time it's the odds that are positive and the evens are negative. So what do I need to do?
N minus 1?
N,
Or plus 1?
probably n plus 1. Because that would probably be something. Because I'd rather start at 0 if need be. Now, how about the factorial? What's the factorial then? N minus 1 quantity factorial. Now here's the part you're going to like. So, an. Remember what an is? It's this guy divided by n factorial. I think I'm going to get some cancellation here. What are we going to get?
Negative 1 to the n plus 1 over n.
By the way, if you'd said n minus 1, that doesn't change anything. That would be fine also. It really doesn't matter. It just as long as you're not odd, you get the odd even. That's kind of a strange looking one. Did I mess that up? Oh, I'm sorry.
Yeah, I
Thank
see
you.
n.
Thank you. Sorry. Over n. So now can we come up with the power series for log x? What is this? Yeah. So log x is equal to the sum negative 1 to the n over n, x minus 1 to the nth power. But where does n have to start? Can't start at 0, it has to start at 1. But also, there's no constant term, is there? The very first term in my power series is going to be the x term. So starting at 1 is not a problem. Okay, you with me so far? This is the power series. So if I wanted to do anything with log, let's say, and I wanted to manipulate. Now, what most textbooks do is they'll say the log of the quantity x minus 1. That way they can write it as an x to the n. I don't like that. I don't like that at all. Because you're never going to work with log of x plus or minus. No, you're going to work with log x.
Did I lose n minus 1?
Thank you. N plus or, it doesn't matter,
Alright,
plus
plus
or
one,
minus.
yeah.
Okay, I'll put plus. Now, where will this converge? I need the interval of convergence. That's kind of huge. So when we do our limit as n goes to infinity, this is an alternating series, but because we're doing absolute value, the negative 1 to the n plus 1 won't figure in. So I'm going to have 1 over n plus 1, x minus 1 to the n plus 1, over 1 over n, x minus 1 to the n. Okay, you with me on this? I don't need this anymore. So when I finish this, I get n over n plus 1 times the absolute value of n minus 1 And that's just equal to the absolute value of x minus 1. And I need that to be less than 1, which will happen when negative 1 is less than x minus 1, which is less than 1, which will happen as long as, wow, that's a very small interval. Didn't e to the x sine x and cosine x give us the whole number line? This only gives us from 0 to 2. Wow, that's not much, is it? 0 to 2. All right, let's check the endpoints. All right, so at x equals 0 and at x equal, 2. So at x equals 0, I'm going to have negative 1 to the n. And I'm going to multiply that by negative 1 to the n plus 1. This is a little tricky, isn't it? And what would this be? If I put a 0 in here, again, I get negative 1 to the nth power. If I do negative 1 to the n times negative 1 to the n plus 1, won't that be negative 1 to the 2n plus 1? Wouldn't that be the same as negative 1 to the 2n times negative 1 to the first? Well, what's negative 1 to the 2n? 1. So that means this is equal to negative 1. Oh, so I would get negative 1 over n, which is just the negative of the harmonic series. So that will, what? This will diverge. Yikes. Okay, what about n equal 2? So at n equal 2, I'm going to get 1 to the nth power. Oh, that's always 1, isn't it? So I'm literally just getting back the alternating series, which we know converges conditionally. Converges conditionally. So therefore, my interval of convergence is what? 0.
And then get the 2 bracket.
Wow. Log x is, man, log x is not very useful if I want to calculate anything that's far away from 0, right? It's not going to be, or I should say far away from 1. Now, you notice 1 is in the middle because I centered about 1. But that makes it interesting. What about the 2? If I replace, I think this is one of my favorite results of power series because it's, okay. Later on today, the level of cool may hit you not before, after you leave here. And this is dangerous because you might be on the freeway and all of a sudden, whoa, what we did? Be very careful. If you feel the level of cool coming on, get into the slow lane because I don't want any accidents, okay? Because the stuff we're doing is mind-numbing. No, by the way, nobody does this. There's not one thing I did today that I don't believe anybody else is doing this. Literally anyone. I can't find any information on this, which is unfortunate because if you study math at the higher levels or statistics, you use this stuff all the time. Everybody in the class sits there with, deer in the headlights looks because they're like, I didn't study this. And your instructors will go, well, you should have seen this in Calc 2. Well, it's not even in the Calc 2 books anymore. Of course you're not going to see it. Can you tell me what log 2 equals then? Wait a minute. So that would be 1 minus a half plus a third minus a fourth forever and ever and ever. That is equal to the log of 2? Yes, it is. And I believe we did a demonstration just by adding them up. Do you guys remember that in class? I said, let's add up the first 100 terms, the first 1,000 terms. And I think Wolfram actually, if I'm not mistaken, I think Wolfram actually let us do, I need to go backwards. Hold on. Well, let us do, I'm going to use the Wolfram calculator. Wolfram calculator, let's do that one. Ah, there it is, right there. I think we have done this before. Now, oh, you know what? Let me go back. Our exponent, sorry, our exponent was what? It was n plus 1, sorry. That changes things just slightly. There we go. Okay. What does it say?
69315.
Yeah, but what does it say before that?
Log 2.
Yeah. Now, remember what I told you guys before? Unfortunately, that means natural log of 2. Why? Because if I do log, if I do log 2, that's 0.3. So that's obviously not base 10. But if you do natural log of 2, you get those numbers back. So we just proved that the alternating harmonic series gives us log 2. If it was negative 1 to the positive n, then all of these signs are different. And remember, the negative of a log is the log of the reciprocal. So the negative of log 2 is the same as log of a half. That's why it would be negative if I did it the other way. Isn't that crazy? Yeah, that's kind of cool. So we're using series to be our calculator in a sense. Now, sometimes if you have a graphing calculator that does integration, sometimes you can ask it to do some of the things that we did for a definite integral. And it will give you a numerical, no, that'll give you something worthwhile. Problem is, your graphing calculator, if you ask it to do the integrations like e to the x squared, it's not going to give you anything because that doesn't have an antiderivative. You see, so it's only really useful if you're doing, let me go back to the integrate. So now, what if I just want to integrate this?
What was that?
By the way, this isn't, I don't think this gives me 7 answers. Oh, okay, okay, I love this one. That's an, oh, not a 0.
Imaginary number.
That's an imaginary number. Yeah, I told you Wolfram gives you some crazy answers. By the way, there's another answer. This is the best one.
What's ERFE?
It's actually ERF.
ERF?
It's ERF of I X.
ERF?
ERF, how many are engineers here?
No.
That's the only place, it's an engineering, it actually means error function.
What?
And you will call it ERF of X.
ERF?
But this is worse, that's an I. It's not ERFE, it's ERF
Imaginary.
I, imaginary of X. Would you say that's a very useful
No.
answer to you? No. If you're an engineer, is that a useful answer? No, because you can't do anything with it. It makes it appear that your answer is imaginary. Your answer isn't imaginary at all. So again, there are limitations. Well, then why is Wolfram giving me such crazy answers? Because there's no antiderivative. So let me go another one. Okay. We've already done this one today. Oops. Look at the answer.
It's 6.
Am I talking? No, SI. There you go, Chase. Good one, Chase. No, that's a totally different problem, Chase. I actually have a coffee mug that a former student gave me years ago. It's my favorite identity in all of mathematics. Yeah. That's a true identity. Everybody knows that one, right?
Oh my gosh.
What?
That's terrible.
I know. I actually have a mug.
Come on.
Well, if you cancel the ends, anyway. No, that's not 6. That's the SI function I was talking about at the beginning of class. This one makes me kind of laugh. There's no antiderivative. So we're going to define the result as this new function that can't be integrated or calculated because it's going to show up in other answers, which just means I'm going to give you an answer with more complication of things that can't be calculated. So I don't know how worthwhile this one is. I tend to believe that maybe it's not that important. If you're a math person, you never use this kind of notation. The only time I see this kind of weird stuff like the ERF is engineering. Because sometimes I'll get things that I can't answer it, but if I have this, I might be able to look it up somewhere later. I may be able to get a value. We kind of like numerical answers, don't we? All right, so Chase, go ahead and stop that.